Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in Chapter 5, part of this playlist that I'm calling Limiting Distributions. There's 21 pages on this PDF, and I'm going to cover 3 pages in each video for 7 videos. So first, a brief introduction on why we need limiting distributions. And in many variable transformations, say y of n, which is a function of n random variables, the exact distribution of yn is not tractable. Not tractable means there's not a nice mathematical formula or solution for this transformation. So in this section, we'll illustrate useful results that apply when n is large. These results are based on notations of convergence and distribution and limiting distribution. So first, let's look at a sequence of random variables. So consider a sequence of random variables, y1, y2, etc., with corresponding sequence of CDFs, and that stands for cumulative distribution functions, capital G1 of y, capital G2 of y, and so forth, that for each n, this CDF is this. So capital G sub n of y is the probability that yn is less than, that random variable is less than y. Now, so if each yn is distributed with this distribution for each n from 1 to infinity, and for some CDF capital G of y, notice that this capital G does not depend upon n. The limiting distribution of our sequence of CDFs equals this G of y, which does not depend on y, and this is for all values y which G is continuous. Now note this here, it's going to come back when y is continuous. Then the sequence y1, y2 is said to converge in distribution to y, where y is distributed as capital G of y. And it's denoted by yn converges in distribution to y. That little d above this means it converges in distribution. The distribution corresponding to the CDF G, capital G, is called the limiting distribution of yn. So some quick examples. Consider a random sample size n from a distribution with CDF capital F of x, which is 1 minus 1 over x. And this is for x greater than or equal to 1 and 0 otherwise. So let's derive the CDF of the smallest order statistic, y1. Now remember the notation x of, and then in parentheses 1, that means the first order statistic. And to ease our notation, I'm just going to call it y1. So the CDF, so this would be capital, f sub y1, of y, or just written as in probability, is this. Now, since it's the minimum, the trick is to look at its complement, 1 minus probability that y1 is greater than y. Now, if the minimum is greater than y, that means every data point in our sample has to be greater than y. So it's the probability that every data point, the y1, y2, yn is greater than y. But the probability that xi is greater than y, we can look at its complement, 1 minus the capital f of y. But this was the formula, 1 minus 1 over x. When we plug this in, we get just 1 over y. I said x, but y, 1 over y. Now notice there's no index on this. So it's multiplied by itself n times, and we get this. And so this is the CDF of the smallest order statistic. And this is for y greater than or equal to 1. Now let's plot some of these for different values of n. So when n equals 1, this is the CDF, n equal 3, n equal 5, n equal 10, n equal to 100. You can kind of see the pattern. As n increases, it keeps getting shoved into this top corner. So it almost looks like eventually it's just going to be vertical and then horizontal. And that's the trend that we're seeing from this CDF of the smallest order statistic. So now let's find the limiting distribution of the smallest order statistic. And we kind of have a hunch what it's going to look like, but let's derive it. So the limit as n goes to infinity of the CDF of y1, which is the smallest order statistic, so it's probably that y1 is less than or equal to y, is the limit of, and this is what we derive for the CDF, 1 minus 1 over y to the n. Now as n goes to infinity, notice that y has to be 1 or more. And if it's 1, this is 1 over 1, 1 minus 1 is 0. But if it's anything greater than 1, this fraction is less than 1, and if you keep raising it to certain powers, it goes to 0, so then it goes to 1. So if y is less than or equal to 1, it's 0. If it's greater than 1, it's 1. That's the limiting distribution of the minimum order statistic. But, however, this is not a CDF, so this is not the answer yet. Now notice in the formula I said when G is continuous at y, notice at 1, this function is not continuous. For values less than 1 and greater than 1, it is continuous, but at 1, it's not continuous. So that theorem doesn't apply to this function at that point. So we can change it however we want. So look, we're going to take this equal sign and put it on here, right? So all we did was switched it. And now the limiting distribution of this CDF, we're going to call this. And this is a CDF. And CDF means it's non-decreasing and it's right continuous at every point. And this is. Now notice that it's a degenerate, what's called a degenerate distribution, and we'll define that a little bit better. But remember this, if we take the derivative of the CDF, we get the PDF. So this is a PDF with 1 point, and all the mass is at 1. So let's find the limiting distribution of the minimum order statistic raised to the nth power. So the PDF is the probability that y1 to the nth is less than y. So we take y1 less than, we take the nth root of both sides, but we do the trick where we look at its complement, and then since it's the minimum, all of them have to be greater than it. So I skipped one step, but we got to here. Now the probability that each xi is greater than this, we look at its complement, which is 1 minus the CDF, and we derived the CDF of the minimum order statistic right here, and so no, this is the CDF, I'm sorry, this is the CDF of x. So we plug it into the formula, which is 1 minus 1 over x. The ones cancel and we're left with 1 over this value that we plug in. Now there's no index, this gets raised to the nth power here, and that is the nth root and the nth power cancel each other, and we're left with 1 minus 1 over y. This is for y greater than or equal to 1. And so that's the CDF of the minimum order statistic raised to the nth power. And if we find the limiting distribution of it, we take the limit of this CDF. So we take the limit of the CDF that we just derived. Notice there's no n here, so it never changes, right? So the limit is, the limit of a constant, So it's this, and it's just for y greater than or equal to 1. Now, a definition and one theorem, then we'll call it quits for today. The function capital G of y is the CDF of a degenerate distribution at the value y equals c if this is the CDF. It's 0 if we're less than that constant, and it's 1 if we're greater than or equal to that constant. So thus, capital G of y is the CDF of a discrete distribution that assigns probability 1 at the value y equals c and 0 otherwise. So this is the CDF of a degenerate distribution. Now, two properties that we're going to use throughout this playlist is the following limits are useful in many of the problems that follow. And so it's the limit of 1 plus c over n raised to the nb. That's equal to e to the b. Now notice that as n goes to infinity, This inside goes to 1 and this goes to infinity. And 1 to the infinity is an indeterminate form. So you have to use a mathematical trick to find this limit. And it's e to the BC. I'll point you to a video that I have that proves this. Another form is this: if we add another term in here, so it's some function of n over n, but this function of n has to limit to 0, and this goes to infinity, this goes to 0, so this term goes away, and we're back in this previous setting where this limit is e to the BC. I have a video that proves this, and this is the title. And so we're at the bottom of page 3, so I'm going to quit and we'll pick up here in the next video. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.